Let's talk a little about why enriching your life with statistics studies will open new doors for you. To name but a few of the possibilities of career choices available for a statistics graduate: actuarial analyst, data scientist, statistician, or statistical analyst, economist, and financial analyst. You might note that this list includes a wide range of career choices in a variety of industries. Reason being that statistics can be applied to most fields where there is data available to analyze. Use this course as the starting point to your statistics learning journey, and remember to continuously aid that journey with both theoretical and practical knowledge as you walk along that path. Good luck, and thank you for choosing this course as your starting point into the world of statistics. Hello everyone, and a warm welcome back to Shaw Academy. Conrad Hilton said that successful men and women keep moving. They make mistakes, but they don't quit. If you feel like you're learning and moving slowly, that's okay. But don't quit. Keep on moving. Just to remind you, my name is Nina Smith, and I am the presenter of this course. This is your professional diploma course in Statistical Analysis Lesson 7. Today's lesson is the start to estimation and hypothesis testing, techniques that we use to make inferences about the data. Today's lesson will kick off with defining and describing estimation. Thereafter, the lesson will aim to explain confidence intervals. And by the end of topic 2, you should be able to interpret and to some extent utilize confidence intervals in an example. The final topic of the day will illustrate the concepts of hypothesis testing, where we will learn more about the process of hypothesis testing and conduct a demonstration in SAS Studio to solidify our understanding of the concept. Let's commence the first topic of the day: estimation. In the previous lesson, we've touched on the concepts of estimation and hypothesis testing, but up until now, not really further extracted useful information about these concepts. We can quickly refresh our understanding of what these concepts are before we start breaking them apart. Parameter estimation and hypothesis testing are two approaches we use to make inferences about the population from the sample data given. An estimator can come in the form of a single value or a range of values. Say we have to deduct information about the cholesterol levels of a population of men above the age of 60 years in a North American state. We can sample a proportion of population and extract information like the mean cholesterol level from the sample. This is referred to as a point estimate, but more on this a little bit later. So what constitutes a good estimate? Meaning, what properties does an estimate need to be constituted as a good estimate? First and foremost, an estimate needs to be as unbiased as possible so that inherent errors do not occur. An example of an unbiased estimator for a sampling distribution would be if the mean of the mean values of the sampling distribution is equal to the population mean. Did you catch that? Not the mean of one sample equal to the population mean, but the mean of many samples taken. Another characteristic of a good estimate is an estimate with a minimum variance or low variance. This concept, a small variance, means that there is little variability from one sample to the next. Now we can return to the original point we briefly touched on earlier: forms of estimation. So we already know that estimators can be used to make inferences about the population, which means that it is the process by which we acquire information and draw conclusions about populations from samples. Parameters describe the population, and sample statistics describe the samples. The sample statistics are almost always unknown, and as a result, we take a random sample of the population to obtain the sample statistics we need. Two forms of estimation that we can use to draw inferences about the population are point estimates that show the most probable value for the parameter, and interval estimates. For example, confidence intervals for the parameter. Remember, all the summary notes and slides are available in your toolkit and would really be worthwhile to keep as a resource at your fingertips beyond this course. But no sneak peeks. The lesson notes will only become available after you have attended your class or caught up with the lessons. These will also help you prepare for your assignments. Next up, we will introduce confidence intervals. Many of you will be familiar with this concept, but did you know that most often in society, it's a concept misused? Confidence intervals is an interval estimation around a point estimate, like the mean. The most common confidence intervals are 95% and 99%. For instance, we are 95% certain that the mean will lie between these determined values. A confidence interval is a range of values that contain the unknown population parameter. In other words, this interval is likely to contain our population parameter. For example, if we sample the same population many times and achieve point estimates on each occasion, the confidence interval would bracket the true population parameter in approximately 95% of the cases. Confidence intervals are used to measure the uncertainty or certainty of a sample method. In other words, to make an observation about an unknown population. You might have heard the phrase, "We are 95% certain that Group A falls within these ranges." This statement is just another way of saying that the population parameter of interest is contained within the 95% confidence intervals in the vernacular. Sometimes confidence intervals are also referred to as the margin of error. So it is important to know more about confidence intervals because this interval can be used to measure uncertainty by providing us with a level of certainty that the population parameter falls within specific ranges. It therefore provides us with more information regarding the sample mean and standard deviation, assuming that we have a normal distribution. Confidence intervals are often misinterpreted. A confidence interval is not the percentage of data from a given sample that falls within the interval. We cannot say that when we draw a sample from a population at a 95% confidence interval of A to B, that 95% of the data from the random sample falls between the upper and lower bounds of the interval. In order to do so, we would need to know the sample mean and standard deviation and be able to identify the sample distribution as normal. We will now head on over to SAS Studio to explore the concept of confidence intervals practically. I'd like the first demonstration of the day to take it back a little bit and use what might be considered a more old school method by manually creating our data set. I want to show you how to do import data this way so that you know that it's possible to do so in SAS and that you do not always need to have an existing data file in a SAS library to import a data set into SAS Studio. Okay, so first we will name our data set. Let's call it scores. Then we name our columns that we want the data set to contain. The column names we can call are grades and gender. We are creating a data set with columns grades and gender. Data lines is the statement that will indicate to SAS that the next piece of code is going to be the actual data. Note that the data set that I want to create is a mock data set. This is not real data. I'm creating this data set for the purpose of showing you how to use confidence intervals in SAS Studio. Our mock data set will contain the grades of students and the gender of the students. Gender will be male or female, and grades can range from 0 to 100%. So let our first student achieve a 60% mark. We will label students 1 for female and 0 for male. We use this categorical labeling just so that it's a bit of easier to work with, as it's a categorical variable. Now let's say the second student was also female and she achieved an 80% mark for the test. The next student can be a male and he achieved a 75% grade for the test. Next student, 40, and female. Okay, I think that's enough data points for the purpose of this exercise. Then we tell SAS that we want to print the data lines that we've created with a proc print statement. And once we insert a run statement at the end of code in SAS, we are letting SAS know that we wanted to execute all the above statements. Now that we have created a data set, we can extract upper and lower confidence limits with the help of the proc mean statement. So we've used the proc mean statement before to conduct some descriptive statistics, so you should be familiar with it by now. You should also know now that you need to specify the data set that you are using. In other words, the data set that we created, called scores. The statement LCLM is the lower confidence limit, and the statement UCLM is the upper confidence limit. We specify to SAS that we want to work out the upper and lower confidence limits for the grades column. And then we insert the run statement, and that lets SAS know it needs to execute the above statements. In the results window, we observe the lower confidence limits for both female and male with a 95% confidence interval. So, in other words, if we extract a number of samples from the data, then the 95% confidence interval will have bounds 47.7 and 85.96. Maybe now we would like to know if the confidence intervals for males and females look the same. We can specify the confidence intervals by gender. Click on Run. Now we note that an error has occurred. If we navigate to the log pane, we see SAS shows us data set work score is not sorted in ascending sequence. The current by group has gender equal to 1. And the next big group has gender equal to 0. So in other words, SAS doesn't like that we've not sorted on the gender column. Therefore, we need to input a procedure that sorts by gender before we calculate the upper and lower limits by the gender. The procedure that we use is simply called proc sort. We sort on the scores data set. We sort by gender, and we execute this procedure with a run command before SAS reads the next procedure. Running the entirety of the code results in the confidence intervals being shown by gender, where gender equal to 0, which we categorized as male, and by gender equal to 1, which we categorized as female. And that is how you perform a quick and easy upper and lower confidence limits method in SAS, using a dataset manually created. Coming up in the final lesson for our first module, we will explore and investigate hypothesis testing concepts surrounding small and large samples. By the end of this lesson, you will be able to identify which procedure to use for a variety of different scenarios. Lesson 8 will end by tying together the practical concepts explored throughout Module 1 and offer some new tips and tricks for data management in SAS Studio not yet explored. It's that time of the lesson again, where we take a short breather before we continue. Let's all take a few seconds to step away from the desk, stretch, and breathe. Here is a prompt for you to follow. You can breathe with a guided animation if that helps you. Feel free to keep it near you whenever you need it through the day. Give yourself a pat on the back for completing 2 of the 3 topics for this lesson already. The final topic of the day will introduce us to hypothesis testing, on which we will further elaborate on in Lesson 8, as we mentioned earlier. So let's first get on the same page. What is a hypothesis? According to the dictionary, a hypothesis is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. In other words, a hypothesis can be a question that is posed by us, the researcher. And from that question, we want to make inferences about the population. Therefore, a hypothesis can be a claim or question that we want to test. There are a lot of different cases that you have to consider when dealing with hypothesis testing. But for today's chunk, we will first focus on hypothesis testing about the population mean. Let's do things a bit different today and first get a bird's eye view of the steps of hypothesis testing and then delve deeper into each concept. Don't worry if you don't understand each concept as they're introduced. We're just introducing each concept so that we become familiar with the language, so to speak. And then we will dive deeper into each one. The first step in our test would be to establish the null and alternative hypothesis. Thereafter, we define the critical value that defines our rejection and acceptance regions. We calculate our test statistic, and finally, we draw a conclusion by either accepting or rejecting the null hypothesis. Our step 1 is to establish the null and alternative hypothesis. The null hypothesis is the value we currently accept as true. We can denote this as H0. Now we want to determine if the null hypothesis is true, and we test it using the alternative hypothesis. This is denoted by HA. Now, when testing the hypothesis about the population mean, the null hypothesis would be equal to a certain value, and the alternative hypothesis would show a difference to the value. Now, we can have 2 possible outcomes to the 2 possible outcomes we have created. We can either reject the null hypothesis, or we can fail to reject the null hypothesis. The reason why we do not accept the null hypothesis is because we are merely stating that we believe the null hypothesis to be more true than the alternative hypothesis for our current set of data. So how do we determine which hypothesis to reject? This decision to reject or not reject is based on information contained in a sample taken from the population that we divide into an acceptance and rejection region. The point dividing the region is called the critical value. The normal distribution shape will always be a bell-shaped curve. So whether we have a sample with 40 observations or 50, the distribution shape stays the same. Therefore, when considering critical values for the normal distribution, these will always remain the same at the various confidence levels. So if we want a 90% confidence level in the test for a normally distributed population, we would have an alpha value of 0,05 and critical values for the two-tailed test of plus minus 1,645. For a 95% confidence, the critical values would be plus minus 1,96. And for a 99% confidence, the critical values will be plus minus 2,575. The critical value divides the sample space into a rejection and acceptance region. It creates a cutoff line, so to speak. We typically set this cutoff at 10%, 5%, or 1%. So if the sample statistic, like the mean for the sample, lies in the acceptance region, then H0 is not rejected. Or if the sample observation lies in the rejection region, then the null hypothesis is rejected. The picture on the right-hand side represents different tests available for hypothesis testing. A one-tailed test for the left tail, a two-tailed test, and a one-tailed test for the right tail. We will explore these tests more in detail in the next lesson. Okay, moving on. We calculate the test statistic from the sample data and use it to determine whether to reject or not reject the null hypothesis. A test statistic measures the degree of agreement between a sample of data and the null hypothesis. The general formula for the test statistic in this course will be test statistic equals sample statistic minus hypothesized parameter over the standard error of sample statistic. We calculate where the test statistic lies and if it lies in the rejection region, meaning if it's past the critical value. We would reject the null hypothesis and say that the null and alternative hypothesis is more likely not the same. The larger the value of the test statistic, the more likely it is that the observed differences reflects a true underlying difference. That is statistical difference. Our last step would be to either reject the null hypothesis and accept the alternative hypothesis. If the test statistic falls in the rejection region, we will reject the null hypothesis as a result. We conclude that there is enough evidence to infer that the alternative hypothesis is true. Or, the other outcome would be to not reject the null hypothesis. If the test statistic does not fall in the rejection region, we do not reject the null hypothesis. We conclude that there is not enough evidence to infer that the alternative hypothesis is true. Once again, we never state the conclusions with absolute certainty, and therefore we do not say that we accept the null hypothesis. Let's pop over to SAS Studio for the last time today to explore hypothesis testing practically in this application. For the final demo of the day, we are once again going to have a look at our Framingham Heart Study data. Let's navigate back to this data set again. It is stored in SAS Studio Libraries under Heart. And if you double-click on the Heart data, SAS will open up the data set. And if we then click on the maximized view icon, SAS will expand these views. We're also able to return to the split view, where the panel with options is on the left-hand side and the data set on the right-hand side. If you remember, I mentioned that the study was done a long time ago, 1948 to be exact. And the aim of the study was to determine which factors, such as diet and exercise and certain medications, impacted hypertensive or arteriosclerotic cardiovascular diseases. These are heart diseases. We saw that one of the variables contained in this data set is the cholesterol variable. The cholesterol variable measures the cholesterol level of the patient, and it measures the cholesterol level of the patient in milligrams per deciliter. So if we conduct a quick summary statistics on the cholesterol variable by using the proc means procedure in SAS, and we say to SAS that we want to see the mean, the first quartile, and the third quartile, the result that we then achieve is in table format. And it shows us that the maximum value, that is the maximum cholesterol level value, is 568. Let's see if we can just enlarge the screen a little bit to see better. The upper quartile or third quartile is at 255, and the lower quartile, Q1, is at 196. And from the literature, if we go and do a quick search, we find that normal cholesterol levels, or specifically the total cholesterol level falling in the United States and some other countries, lies between 200 to 200 and approximately 40 milligrams per deciliter. So let's assume that anything above 240, for the purposes of this exercise, is considered a high cholesterol level. Let's now conduct a hypothesis test if the mean value for the cholesterol variables observations contained in this SAS dataset, meaning is the specific sample's mean greater than 240? Did this study also find that 240 is a higher than average amount for the cholesterol levels, like what is found in the population of the US and other countries? We can test this hypothesis by conducting a hypothesis test. So let's now assume that anything above 240, for the purposes of this exercise, is considered a high cholesterol level. Let's now conduct a hypothesis test to determine if the mean value for the cholesterol variables contained in this SAS dataset is greater than 240. Did this study also find that 240 is a higher than average amount for the cholesterol levels, like what is found in the population of the US and other countries? We can test this hypothesis by conducting a hypothesis test. The hypothesis test we can find in the right-hand side panel under Tasks and Utilities. We navigate down to the t-tests. Just a note, don't worry too much about the naming conventions right now. The purpose of this exercise is to get you familiar with hypothesis tests and using them in SAS Studio. In the next lesson, as I've mentioned before, we will dive deeper into when to use each specific test and when to use one sample test. When should you use a two-sample test? When is a sample considered to be large or small, and so forth. So the data set that we once again will use in the SAS help library is the HEART data set. We will conduct a one-sample t-test. The reason I'm choosing a one-sample t-test is because our null hypothesis is testing if the mean of the specific HEART data sample is bigger than the value of 240. So yes, that is the hypothesis that we test. Again, our null hypothesis and the analysis variable that we're using is the cholesterol variable. We want to conduct, as I've mentioned, an upper one-tailed test. We're choosing the option where mu is greater than 240. Should we have chosen lower one-tailed test, we would have assumed that the mu value is smaller than the 240 value that we're choosing. But we are testing if the mean is greater than that. That's the conjecture that we're conducting testing against. Finally, let's include tests for normality. We can also choose to include the histogram and box plots. And as you can see here in the coding pane, the procedure that SAS uses for conducting an upper one-tail test is called proc t-test. If we deselect the normality and the histogram box, we notice that SAS has now disposed this part of the code. Therefore, we note that this part of the code tells SAS to create the histogram and box plots. The tests for normality is therefore contained in the proc univariate statement. So this statement here contains our tests for normality. So the tests for normality is coded as the procedure, proc univariant. And the t-tests are coded as the statement under proc t-test. And running this code by clicking on the Running Man icon, SAS will spit out some results for us. I don't want you to worry too much about how to conclude the results right now. We can focus on that in the next lesson. That is the basics of how you can conduct an upper one-tail test using SAS Studio. As we get to the end of Module 1, I want to take some time to remind you about your learning path with Shaw Academy. No matter why you decided to sign up for this course, we strive to teach practical skills for everyone. Whether you are a hobbyist looking for a course for every level of learning, or a professional looking for crafted learning materials to up your game, or perhaps you're an entrepreneur looking to build confidence in multiple areas. Whoever you are, we have a course for you here at Shaw Academy. Don't forget that coming up next week is the start of Module 2. Remember to book your spot now to avoid disappointment. We have many membership options available, and there will definitely be one that is well suited to you, no matter who you are. Thank you for joining me for Lesson 7. See you soon for the final lesson of this module, Lesson 8. You are doing great. Don't stop moving forward.